I'm in an awkward spot because I'm standing between you and the main event, right? So I'll try to keep it as short as possible and take it on from there. So I'm JV Rajendran. I am an associate professor at Texas A&M University. Interestingly, I'm a professor in the electrical and computer engineering, focusing on security. Right? Traditionally, we view security as a computer science, software, network type of topic, but security also spans to many electrical engineering. What I'll be focusing mainly on is security of chips. And then at the very end, I have something interesting that is more attuned to the Houston crowd. So hang in there. I would like to acknowledge my sponsors, mostly Sandia and Navy, for sponsoring the bulk of the work, and then my industry collaborators, Intel, Synopsys, Lockheed, for helping me with the designs, tools that we will be fuzzing and so on. And almost all the work is performed in collaboration with my partner, Professor Ahmad Reza Sadeghi at TU Darmstadt, Germany. Okay, so I direct the secure and trustworthy hardware lab at Texas A&M. So our focus is on hardware security. So we have like 4 important topics. So first one is the supply chain security of electronic systems. So how many of you think the chips designed in US are manufactured in US? Okay, great. This is a great crowd because yes, they are not manufactured in US, they are manufactured somewhere else. But our entire infrastructure relies on the trustworthiness of these chips, right? And what my lab does is it develops techniques so that you can build that assurance that these chips are not tampered with. They don't contain any malicious components, aka Trojans, in them, and so on. And that is our supply chain security. And then we also, how many of you participated in capture the flag competitions? Okay, great. So we ran the world's largest hardware security capture the flag competition called Hack the Silicon. So we give hardware designs riddled with security vulnerabilities in them and ask participants to identify them. Right? Probably we are the only silicon developers who are proud of having so many bugs in their designs. And hardware fuzzing is what I'll be talking about. So which is more of a technique on that we have been developing in the last 6 years in my lab on catching these security vulnerabilities. And finally, we do use AI, but mostly in the offensive sense. So we develop AI to develop automated attacks. So whenever someone publishes a paper that doesn't do a good job, I used to ask my grad students to write a counter paper, but these days I use I build an AI agent that can develop the counter technique and write the paper by itself. I should soon replace AI with large language models, but that's an ongoing project. So while I'm here, almost all the work is being performed by my students. So I have students ranging from PhD, master's, bachelor's, all the way to high school in my lab. This is just a subset of the students who perform who perform the hardware fuzzing work, but then there are other students looking at other security problems and cryptographic accelerators and so on. So, any IDs in the room? Any long arms in the room? No. Okay, good. Okay. Now, so if you look at the landscape of trusted computing, there are vast majority of solutions. I don't expect you to read each and every word on this slide, but what you want to understand is that more and more security features are being pushed from the software into the hardware. And this is because hardware can support more number of transistors these days, and they want to open up more hardware features to the end user, and that is why you see more and more hardware features have more and more hardware silicon chips have security features in them. But of course, things are going to run a lot faster, cheaper, low energy in hardware compared to the software equivalent. And so you have like trusted execution environments. Many of you may be familiar with that. You have security, embedded security processes, dedicated security chips, runtime protection capability mechanisms and things. And many of these solutions, while coming from academia, but there's also coming a lot from industry, and there is a good amount of risk-free community that also develop these things. So bottom line, there is a lot of security stuff happening at the hardware silicon level. But then we ask a question, especially coming from an electrical engineering department. Hey, we design hardware code. So if you look at the piece of code that is out there, that is the Verilog code. So there is a hardware description language. It is how you describe what the hardware should be doing, right? So we usually say like, hey, most of the software vulnerabilities happen because programmers write buggy programs. And we hardware engineers are no saints. When we design hardware, there's a lot of bugs that we inject, and increasingly because more and more hardware features are exposed to the end user, increasingly the mistakes in hardware are being exploited, right? And that is the question that we ask, hey, is this code secure? Right? Obviously the answer is no, otherwise I wouldn't be here. And this is a problem that has been facing the semiconductor industry over at least in the last 2 decades, right? So this is not a new problem. How many of you have played with FPGAs, Raspberry Pis, and things like that? Okay, great. Okay, so if you think about how those pieces of hardware are designed, so usually what companies do is they undergo this hardware development lifecycle. The idea here is they will think about your product, they'll think about your concept, and then see like, hey, what type of design I should target for this particular market. So for example, and then they do like architecture planning, think about like how many number of cores, what is the memory architecture that they want to use, and so on. And then they implement a microarchitecture, and then till microarchitecture, everything will be like, think of it like block diagrams with parameters. But then during the RTL implementation is when the conceptual idea gets into realization. So that is when you have chip designers writing several thousands of lines of code, and those lines of code are the one that gets synthesized and translated into silicon, right? So, and of course, they are going to have verification steps to make sure the code that they, and I'm using the term code in a very loose fashion. They use the code to verify the code to see it is devoid of bugs, it is devoid of functional problems, and so on. And as and when they are happy, they send it for fabrication, so meaning the code gets translated into an actual silicon chip. So what you realized in what you designed in the code, that gets translated into the actual product, right? And then they test this chip for manufacturing defects, and then if they are happy, then they ship it to the market. And of course, they will never test for all possible problems. You can ask Intel people, right? So, but then again, I'm not even talking about like security problems. I'm only talking about like manufacturing problems until this point. But then security problems do arise. So, for example, as and when people are writing this code, when they think about the conceptual idea of this design, they unintentionally introduce bugs, right? Because many hardware engineers, they are not trained on with a security mindset. Right? If you go and pick a university curriculum for electrical engineering or for computer engineering, it's very rare that they will be exposed to security concepts, let alone hardware security concepts. And because of this, they do introduce many unintentional bugs and flaws, and increasingly they do get exploited. So what companies have done in the last 10 years or so companies like Intel, ARM, AMD, and so on, what they have done is they hired a lot of security engineers. And these guys, they develop something called the security development lifecycle. So as and when the chip design is being done, the security team sits together with the development team, and then they say, hey, how do I, what type of attacks that this chip will face? They do the threat modeling, they understand what are the security assets that are there, how they need to be protected, and so on. And then they sit with the developers, literally over their shoulders, looking into their code, right? And they do the manual analysis. They also do simulation to make sure the chip doesn't do anything bad. And then when the chip comes back, they do a lot of testing, usually negative testing, the type of testing that designers haven't thought about. Like, for example, they will apply instructions like multiply 0 times 0. Everyone knows the answer. You will never execute 0 times 0 in your hardware if you have a good compiler. But yeah, the security people are like, okay, I want to see what happens if I apply 0 times 0, or even better, 0 divided by 0, right? And see if the hardware cranks up, if it crashes and things. So that's the type of negative testing that people do to catch many problems, and then but sometimes problems do skip these checks. The bugs do skip the checks, and they end up and the chips get deployed in the real world. And how many of you heard of the two famous words, meltdown and spectre? Okay, so those are for people who don't know. So those are the like classical security problems that creeped up. Maybe I would say like top 5 security problem in the last 7-8 years that kind of shook up the computing industry, and people and I'll talk briefly about it. It took a large coordination among chip manufacturers, operating system providers, software developers to actually patch the problem, because the problem was in silicon, and once you cannot change the silicon, right? Like think about it like you have a, how many of you drive Cybertruck? I should not be making such jokes. Okay, so so if there is a problem in a car, it gets recalled. But if you think about the same way, if there is a problem in silicon, you can only way to fix it is you have to replace the silicon, right? There is a more expensive way, which is you patch the software running on the silicon so that you never get to use that feature, right? So for example, after Spectre and Meltdown, Intel shut down the simultaneous SFT technology that they had. Okay, so what do we do? So people have been worrying about this problem. They developed a lot of approaches. So many of these approaches are coming from the software security domain, because we hardware engineers are very creative. We say like, hey, we don't need new solutions. We just go and see what the software people have done and see how to apply it for hardware, right? If that works, then our job is done, right? And if you look at the, and there is also a very good reason why hardware security people do that, because software security has been leading the hardware security community by at least a decade or so. So they are more advanced, they have a lot of advanced technologies. So it's more like an Occam's razor. When you have something, why use it, and why do you want to invent something new, right? So that is the idea here. So there have been a lot of approaches that use proof carrying code, model checking, information flow tracking, and so on. And these are like formal, heavy hitting approaches. They just do not scale well for hardware, because in hardware you have like billions of transistors sitting on the chip, and if you want to run a formal engine on these things, good luck, you will never complete before the universe dies. So existing approaches basically do not work. And we said, okay, the academic university professors, we are always like full of exciting ideas, or I mean, we say we have the ideas, but usually it's the students that have the ideas. And we want to solve this problem of finding security bugs in chips. But then there was a big issue that we don't know what these problems look like in actual silicon, right? Yeah, why? Because unlike software companies that say, here is the piece of code that is problematic, hardware companies will never show their designs that is problematic. Intel will never share their code, say, hey, here is a problematic code, right? But, so we did not have good examples. Only when you have good examples, you will have a good understanding of the problem so that you can develop solutions. But companies, for good reasons, they won't share their source code and so on. And that was an issue. And we tried to solve this problem by creating our own designs, right? So what we do is there is a lot of open source designs, mostly developed by academics, but also now by a lot of like small companies. There's a lot of them in the RISC-V community. And we sit with our friends at Intel and we say, hey, here is the open source designs. What kind of vulnerabilities would you see in this, right? So based on our Intel friends, based on their experiences inside Intel and the type of vulnerabilities that they see in their product, that they fixed it and so on, they will replicate the similar set of problems in these open source designs. And then we release these open source designs out in the public for academic researchers to study, to analyze, to develop defense techniques on it, right? And so this is led to the creation of the capture the flag for hardware people, and we call that the hack the silicon. It has been successfully running into the 9th year now. And the goal is to promote hardware security verification. It's the world's largest hardware security competition. A lot of companies partake in it, and success is like it has trained around like 1,000 hardware engineers who are traditionally not exposed to security. It helped detect like close to 1,000 vulnerabilities in products. And again, I know like 1,000 may not be a large number for if you are in software or network, but we don't, in hardware, we don't have those many designs, right? So finding problems for us is very critical. And we have like more than 10 instances of the competition. So if you are in hardware, if you're interested, please do sign up. Okay, now going back to what I want to present. So how many of you heard of the MITRE database, CVEs, CWEs, and so on? Okay, great. So in US, if you are a company, it doesn't matter hardware, software, network, and so on. There is a mandate that if your product has a problem, you should report to the US government, right? And that problem, in a very abstract sense, will be available in the National Vulnerability Database. And of course, you need to work on how to patch the problem and so on. And this is a mandate for any US company, as well as if you are a company that sells your product to the US government. And this database is owned by NIST, and it is maintained by MITRE. And what I'm showing here is the number of hardware-specific vulnerabilities in the last few years, right? And as you see, the last 7 or 8 years, the number of hardware vulnerabilities almost doubled in this National Vulnerability Database. So how many of you heard of Moore's Law? So in chips, there is something called Moore's Law, which is the number of transistors in a chip tends to double almost every 18 months to 2 years. And this law has been holding true since 1970s. And then some people say it died in the 2018, 2019 timeframe. But then what I call this as Moore's Law in zombie mode, because even though the hardware doesn't grow, the problems in hardware keep growing. Yeah? And why hardware vulnerabilities are difficult? Because you cannot patch them. Unlike like software vulnerabilities where you can release the patch, hardware vulnerabilities, the only way to actually fix it is you have to recall the chips, right? So our friend at data centers, think about the amount of effort that they do, and then I go and say, hey, now you have to replace all your Intel chips in the servers. They're like, good luck. Yeah. And now the question is, hey, can we detect these vulnerabilities before the chip goes into production? Because we know that once it has been manufactured, it is too late, it's too expensive to fix the problem, so we want to catch them at the design stage. So what we are looking for is two things. One is completeness and time. So completeness, in roughly speaking, is that I want to capture all the security vulnerabilities. Or differently put, I want to make sure my hardware does not have any security problem. That is the completeness. And time or effort is basically I'm too lazy, I don't have resources, but I have to have something that makes my life easier, and I want to do this verification a lot quicker, right? So on one end of the spectrum, you have random testing, where you can run it a lot faster with relatively less effort, but it cannot give you any completeness guarantee. It cannot give you many mathematical guarantees that your chip is devoid of problems. On the other hand, you have formal. It gives you very good completeness guarantees. It says that, hey, your chip will not have these problems, but it is too expensive to run in terms of time, computational resources, human effort, and so on. Right? Ideally, you want something that gives very good completeness guarantees with minimal effort and time. And this is where fuzzing comes into picture, where it's very close to ideal, but again, it will not give you the very good completeness guarantees, but at least it will give you a very good starting point. So again, as I told you before, we hardware security engineers tend to copy from the software security people, and that is exactly what happened. So fuzzing techniques have been developed for software and even for networks, right? And fuzzing techniques have tremendous success in capturing vulnerabilities in software. Here I'm picking one example, Google. And Google has an internal mandate that every code that they write,
they need to be fuzzed before the code gets deployed, right? And there is a very good reason why they do it, because fuzzing is a very good first line of defense, and it can capture many of the problems before you go for heavy hitting tools like formal verification and so on. So we said, hey, and of course this is not just Google, there are other many companies that use a lot of fuzzing, and fuzzing is not just limited to software, people also fuzz network ports and so on. And we said, if fuzzing is so successful in capturing security vulnerabilities in these domains, why not use that to find security vulnerabilities in chips, right? And that is what we did. So it started as a very small toy project for a master's thesis student. And I'm not going to explain each of the blocks in the interest of time, but what I'm going to fuzz is, this is the design, this is the chip that I want to fuzz. And I'm going to apply a random set of instructions. And I don't care whether it is valid instruction, invalid, I don't really care. And I'm just going to see what happens to the chip if I apply random things to it, right? Basically, I'm going to torture the chip and see if there is a place where it breaks, if there is a place where the chip hangs, if there is a place where the chip produces outputs that it's not supposed to do, right? And then I am going to see, while I'm doing this, I'm also seeing, did I hit many different regions of the chip? If I do not hit a specific region of the chip, I'm going to tweak my inputs. It's called the mutation engine. That's going to tweak the input to see if the mutated input can hit the new region or not, right? So I'm going to keep doing this process until I hit enough coverage or until I crash the chip and so on. So what we did is, 4 years ago, we started this, and it started as a very small toy example, and we applied on 3 different chips, and we found many problems. So, for example, there is the first one, Orion. Now it is called CVA6. It's a processor design coming out of ETH Zurich in Switzerland. It ended up in many European commercial products, and this processor implements something called fence instructions, where it allows memory isolation between 2 users. That is, user 1 cannot access the memory regions of user 2, right? But the logic behind this instruction, the part of the chip that implements this instruction is incorrectly written, meaning it doesn't provide the memory isolation that you want to do, right? So that was a problem. And then this MOR1 cape that has been there for like more than, it's an open, again, all these are open source processors. Anyone can look into the code. The MR1K has been there for more than 12 years, but so it has this privilege register that tells whether you are the normal user or the root user. But then anyone can write to this privilege register, because it doesn't check permissions when you want to write to the register. So meaning you can escalate your own privileges by just writing to the register. You don't need to worry about operating system or anything. Okay? Again, this processor has been there for like 10 years with the code open, source code open, but people haven't found it. OR1200 has been there for like close to 20 years. Again, it had a problem that we found with fuzzing. Source code is there, but people haven't found it until we did. And again, I'm going to be very conservative in what I call as bugs. Only the bugs that I can exploit, I call them as bugs, right? And so, for example, this one, we were able to exploit it to perform arbitrary code execution, meaning if you don't have right permissions to execute your code, using this problem, you can execute the piece of code that you are not supposed to execute. For the MR1K processor, you can escalate your privileges. So let's say if you are the normal user, you can escalate yourself to the root user and start doing crazy things, right? And so we were able to find in total like 11 vulnerabilities in three products. 8 of them were new, and then we were able to get 5 CVEs. So for those of you who don't know what CVE is, it's a common vulnerabilities enumeration. So if you find a problem in your product, a security problem in your product, and if you are the first person to find that, you can report to the National Vulnerability Database, and they will assign a number for your finding, right? and of course you need to let the developer know for ethical practices and so on. So we let those developers know, and we were able to get 5 CVs just for this preliminary version. So here is the demo of the MR1K. In the interest of time, I'm not going to show you the video, but it's there, right? Initially you will not have a permission, but then you write to this particular register, you can escalate yourself. And of course, we are able to achieve much higher coverage than existing techniques. So then we said, okay, hey, we are able to capture functional problems. Can we push it further to capture problems like Spectre and Meltdown? So if you look at the recent attacks in Red Hat, Black Hat, and so on, there have been a lot of problems reported on AMD, Intel, Apple processors, even Qualcomm processors, on how they leak the secret key of the cryptographic algorithm running on these designs using timing information, right? So for example, depending upon the value of the secret key, the same cryptographic algorithm may take a little longer, right? And I just look into how much time it took for you to do a certain task, and based on that, I can tell what your secret key is. And that is the vulnerability that were there in these processors. That's called timing channel. And we were able to find such vulnerabilities in many open source processors. So in total, our hardware fuzzing work has around found 14 new problems in chips and 12 new timing problems in chips. We were able to get 7 CVEs. There's a lot of articles highlighting our research. I'll put the link and make the slides available so that you folks can look into it. Okay, so now that I understand this is Houston, not Austin. So Austin is big on chips, but Houston is big on oil and gas and healthcare, right? So for oil and gas, so everyone knows what Stuxnet is, right? There's been a famous attack on the centrifuge system, but then you also have these type of problems hitting Schneider Electric devices. We also talked about so Ukraine had the blackouts caused by malware. We also had the Colonial Pipeline attack and so on. And now the question is, hey, can we prevent these attacks, right? And what my team is looking at is, hey, how do we prevent these attacks from the hardware perspective, right? So what's going on is that if you look at an industrial control system, this is what the hierarchy looks like. You have applications, runtime environment, real-time operating system, firmware and drivers, and then at the bottom is the hardware. But there are a lot of problems in hardware, for example, in the programmable logic controllers, PLCs, that are being used in oil and gas, smart grid, many of the ICS settings. There have been a lot of problems in these PLCs, and that are getting increasingly exploited. And those are some of the vectors that attackers have exploited in the attacks that I listed before. And what we are working on is, hey, how do we find the vulnerabilities in PLCs using fuzzing, right? And that is something my students are looking into it recently. So if you are interested in PLCs, ICS security, I'd be more than happy to talk to. What else do we do at our lab? So we also do a lot of reverse engineering of chips. So we take chips, we peel them off, we see what is inside, right? Sometimes we also develop techniques so that you don't need to do destructive reverse engineering. You can figure out what is inside the chip using non-destructive reverse engineering, and that is another work that we do. So here are the QR code for the papers that I talked about. All the information that I talked about are public. You can look into a set of applications, and I think I'm almost at the point of 30 minutes. So I'll stop here and take any questions. Oh, I have 10 more minutes? Okay.
Somebody wants to ask a question?
Yeah. Yes.
So you're starting to see a lot more of the FPGAs in the digital market now. It used to be it was very popular that everybody buys this one place in the house. More products are going to come out. Is that introducing a level of following vector of threat or modifying the markers?
Yes, so increasingly the FPGAs are entering the market. So for people who don't know what FPGAs are, so FPGAs they allow you to reconfigure the logic that is being implemented. So if you let's say you have a 32-bit adder that you implemented on the chip, so instead of 32-bit, tomorrow you say, hey, I also want to add a subtractor module. So along with the 32-bit adder, you can add a 32-bit subtractor, and also you can reconfigure in the field, right? And this is being increasingly used, vastly used in the DoD defense setting, because they don't want necessarily fixed hardware. They want something that they can reconfigure in the field, because they feel like, hey, if I discover a problem, at least the FPGAs give you the opportunity to update the setting. But FPGAs, they do come at a cost, meaning they are not as fast as their fixed counterparts, right? And they consume a lot more power. But increasingly FPGAs are becoming popular because I can reconfigure them and so on. But the same set of problems also exist for FPGAs. So there is I think AMD has a big FPGA market. There was a vulnerability that was discovered in AMD's FPGA, I think 2 years ago. It's called Starkly, where anyone can upload whatever they have designed instead of the original design. They can replace it with their own design. So they do have problems as well. Does that answer the question?
Yeah, it does. It kind of simply comes to mind. A lot of the hardware that over against the brawl, you had 602, 02 chips that fell into place. It's a very big risk.
Indeed. Yes, please.
Do these have these fuzzing techniques had negative impacts on the chips themselves, or have the chips been kept intact during the process?
So it did not affect the chips. If your question is, hey, did you make smoke? The answer is no. I wish my students smoked a chip, but no. So we haven't set anything on fire yet. But the techniques that we are doing, we are applying the fuzzing techniques on the design of the chip rather than the chip itself. But we do have the capability to put it on the chip. But for some other research, what we do is we torture the chip by putting it in a thermal oven and setting it to fire until like 800 C or something, and see how it reacts. And at A&M, we also have the cyclotron facility where we bombard the chip with heavy ions and see how the chip reacts. So we do torture the chips, yes. Yes.
So you compare the software security as hardware. I'm curious. So in software, we have a lot of problems, specifically because of dependencies, packages that support the supply chain when you're building the software. It looks like, I would like you to talk a little bit more about how that, it looks like it doesn't affect the hardware industry, because it looks like whenever there is a new project, they will write everything from scratch.
No.
They don't share anything. Can you?
No, sharing is caring in hardware too.
Okay.
So what people do is, so hardware industry, they use a concept called design reuse. So what it means is that, let's say you have a company and you produce generation 1 of a design. When you want to use generation 2, close to 70% of the new design is exactly the same as the first design. Okay, so that is called design reuse. That is heavily popular in the hardware industry. And then even another concept is even for companies like Intel, where they have everything, right? And so many engineers and so on. Even then, even the Intel chips, they do not contain 100% Intel components alone. Even for them, they buy IPs from other vendors that specialize in certain components. For example, there are small companies that specialize only in video encoders, audio encoders, so they buy that IP. And recently, there are a lot of small companies on building neural networks on the chip, so people buy that IP and integrate them in their own designs, right? So this type of integration, where you buy IPs from many different companies and put them together, is a very common practice in hardware. So that is very similar to the software industry as well.
And I can assume you guys do the same thing that we do, which is running scanners, hardware composition analysis that's with it, scanners to detect those dependencies on the supply chain, etc. Right?
Correct, but I wish it. You are right. We do perform such dependency and composability analysis, but it is not as mature as what the software industry does. Yeah.
All right, everybody, give a hand.